One of the coolest things about multivariable calculus is using it to solve single variable calculus problems. In particular, sometimes you can take a single variable integral, convert it into a double integral, and solve it that way. The most well-known example of this phenomenon is the Gaussian integral. This single variable integral has no elementary antiderivative, so single variable techniques don't work here. So the classic trick is to take this, square it, and turn it into a double integral. Once we've done this, we have multivariable calculus tools at our disposal, for example, a polar coordinate change. I love this because it feels like taking a long detour to get the answer to the original problem. We seemingly make something more complicated by jumping up into higher dimensions, but then multivariable calculus techniques kick in and make it doable. I want to show you another example of this phenomenon. The example we'll look at will be a little different, but the general principle of using a double integral to evaluate a single integral is the same. So here's what I want to do. I want to evaluate the integral from 0 to 1 of x minus 1 over log of x. I encourage you to try it for yourself, and in particular, see if you can get any single variable techniques to work. You'll find that it deflects pretty much anything you throw at it. For example, we could play around with the idea of making a basic substitution, like u equals log of x, but it doesn't work so well. The only other standard technique that feels like it might work here would be something like integration by parts, but with the logarithm in the denominator, it's really unclear how to set this up in an effective way. But don't just take my word for it, try it for yourself. The familiar integration techniques don't work, and you'll get a sense of that when you play around with this for a while. So then what do? We give up, move on with our life, do something else. Or we figure out a way to cleverly turn this into a double integral and hope that we can use some multivariable calculus techniques to evaluate this. Specifically, here's what I'm going to do. The troublesome thing about this integral is the log of x in the denominator. I want to do something clever to deal with that logarithm. So let's think about this. How in the world could I get a logarithm in a denominator in a natural way? Well, here's a fact to recall from Calc 1. If I have an exponential function, say b to the y for some number b, here I'm thinking about y as the variable, and you'll see why in a second. If I take the derivative of this with respect to y, what do we get? Well, we get b to the y, but then we have to multiply by the natural log of the base b. So what does this tell us about antiderivatives? The antiderivative of something like b to the y with respect to y, reversing this differentiation rule here tells us that we get b to the y with a natural log of the base in the denominator. So a really natural way to pick up a logarithm in the denominator is by integrating an exponential. Here I integrate an exponential with base b, and I get a logarithm of b in the base. In this integral here, we have a logarithm of x. So maybe we want to consider integrating something of the form x to the y. And that's the basis of the trick that I'm about to do. In the original integral that we care about, I'm going to latch on to this numerator first. X minus 1, motivated by this right here, I can rewrite this as x to the y, evaluated at y equals 1 and y equals 0. But now look what we have. This term right here looks a whole lot like this term right here. In other words, this function is the antiderivative of x to the y with respect to y. So running this rule backwards tells me that the inside quantity here is the integral of x to the y from 0 to 1 with respect to y. And with that extremely clever observation, we've successfully turned this single variable integral into a double integral. Now, was this helpful at all? Well, we need to do something in the world of multivariable calculus. We could think about a variable change or something like that, but this problem is actually much more simple. The observation is that integrating this with respect to x is pretty simple. It's a power rule problem. So the multivariable calculus technique that kicks in is simply reversing the order of integration. And since we're integrating over a rectangle, we don't have to do anything fancy with the bounds. We can just flip-flop at will. Now that we're integrating with respect to x first on the inside, I treat this as a power rule problem. The power rule tells me increase the power by 1, divide by the new power. So after evaluating the antiderivative at x equals 1 and x equals 0, I pick up a term like this. 0 to the y plus 1 is just 0, so this whole term goes away. And then 1 to the y plus 1 is 1, so this term just turns into 1 over y plus 1. And we're in the home stretch. The antiderivative here is log of y plus 1. Plug in our bounds. Log of 1 is 0, so that term goes away, and we're left with natural log of 2. And we win.